So problem 1134 talks about the formulas for the input and output resistances for the closed loop case in equations they mentioned 1122 and 1125. And they say that those equations also apply to the case in which the gain, the open loop gain, is a function of frequency. So they were not expressed as such in those equations, but they're telling you that they apply. And of course, now that we're talking about something that is dependent on frequency instead of resistances, we're talking about an impedance. So complex impedances that will be functions of frequency as well. And then they ask you to consider the case of a series shunt amplifier that has an input resistance Ri and an output resistance Ro. So those would be the open loop inputs and output resistances respectively. And then they give you an open loop gain that is dependent on frequency. So the open loop gain always is going to be in the form for most amplifiers, or we try to actually be something that we're going to talk about later called frequency compensation. We're going to make sure that it has if it has multiple poles, that it has a dominant pole, that at least one pole is dominant, that we can regard it as having a single pole. And then it's going to have that form, which is the mid-band gain, which is going to be a flat gain in the passband, denoted as A sub 0 divided by 1 plus S divided by omega H, which is that high frequency pole. They also tell you that it has a feedback factor beta that is independent of frequency in this case. So they are asking us to find the open loop input and output impedances and give an equivalent circuit for each. Together with the values of all elements in the equivalent circuit. Okay, so the first thing that we can do, this is problem 11.4. The first thing that we can do is, or 11.34 rather, okay, is to state those equations that they talk about. So they're talking about 11.22. So 11.22. Just looking from the book, that equation is for the input impedance of the closed loop case times the input resistance of the open loop. So this is open loop, this is the closed loop. So that is for the input resistance. And then the other one, 11.25, from the book, just looking at it, is the open loop output resistance. It's going to be the closed loop output resistance is going to be the open loop output resistance divided by the amount of feedback. Okay, so we're just gonna expand this to the case where A is a function of frequency. So they give us this, so they say now A is a function of frequency, so it's that passband gain divided by 1, and this is the form of a first order filter with that high frequency pole. Okay? So all we have to do is figure this term as a function of frequency. Okay? So that would be so that be simply that, and then if we extend equations 1122 and 1125, we have that the input closed loop impedance is equal to the input resistance open loop times that the amount of feedback, which if you substitute for this, what we have over here, okay, then we get that the input open loop input impedance is and that is our closed loop input impedance that we can also express as an input admittance. So by taking the reciprocal of this and just doing some manipulation, then we get an admittance that is complex and would be so basically just some manipulation. Now if we look at, because they also ask us about the circuit that is represented, and that's why this admittance expression is convenient, because we can see that we have a real part and an imaginary part. We clearly can see that if we substitute S for j omega, and then we can see that that circuit will look as the input resistance over here, and so that is in parallel with a complex admittance over here, which is capacitive in nature. So high frequency poles are capacitive in nature. And then this resistance over here would be and this capacitance would be so of course that we know that there is a minus j there because it's a capacitance, but that would be an impedance. We're just saying what is the value of the capacitor, of the actual capacitor, which is normally the impedance would be minus j over SC. So that's where the S went. Okay, so we're just looking at this quantity. So that quantity is that there. Okay, and we can do the same thing for the output impedance. So by going back to equation 1125, so closed loop output impedance is the output resistance divided by the complex amount of feedback. Well, defined generally as divided by the amount of feedback, but in this case the A is complex. So we substitute our quantity there and we get and that's our complex output impedance. And if we manipulate this to put it in a complex admittance expression, that would look as the closed loop output admittance, which is 1 over Z. That will give us 1 over the output resistance plus like so. That would consist of the output resistance. This expression would consist of an output resistance, and that is going to be in parallel with a series combination of an inductive load and a resistor. So that specific impedance after manipulating that previous expression into a complex quantity that has clearly a real quantity and a imaginary quantity, which will look like a circuit like this. And
can you explain how you made the jump from YOF to Z again?
I'm sorry?
Can you explain again how you went from YOF to Z again?
Just by that's just a algebraic manipulation to make it into a real part and an imaginary part.
Oh, okay.
So you know that always basically it entails getting rid of the J in the denominator, getting a common denominator, and separating the real and imaginary part, and then simplifying. Those are the general steps by using conjugates. So basically, by multiplying by the conjugate, so conjugate over conjugate, and then of the denominator, so this then will become real, the denominator will become real, but then the numerator will become clearly something that you can divide into real plus imaginary over some type of real factor, and then you simplify. That's why they don't look the same, because they're being simplification. Okay? Does that make sense?
Yeah, it does. Thank you.
All right. It's just just tedious algebra, okay? So this over here is going to be arrow. This is going to be arrow A0 beta, and this one, the L, is going to be arrow A0 beta as well. Now the impedance of the inductor, of course, is going to be J omega L. So that's what you're going to end up with. But we're just saying what is the value of the inductor. Okay. So these two come from this part. Okay. And that would be your, as you look into the output, that would be the output impedance for the closed loop case. Just like before, the other circuit, looking into that circuit would have been the input impedance for the closed loop case. So that is problem 1134. Are there any questions about that?
I had a quick question about the input impedance.
Yeah.
Do you do the same transformation from the admittance to the impedance like you did for the output?
No, that one is more straightforward. Well, yes, actually, yes. You do have to put it in that form that you have. So let's say you have an expression. So complex expression 1 over complex expression 2, okay? If you multiply by complex expression 2 conjugate divided by complex expression 2 conjugate, you don't change the expression, okay? We agree on that, okay? But because these two are complex conjugate pairs, what you get is some type of new expression, but that expression is real, okay? And then you get a complex expression. So I should have not, let's just call it R for real, over some complex expression after you do this multiplication here, okay? Then you split C4 into real of C4 plus imaginary of C4 here, right? So then your expression clearly would be a real part, because real of C4 over real 3, right? So we'll get, let's call this real 4, and let's call this imaginary 1. Your expression becomes real 4 over real 3 plus imaginary 1 over real 3, and then you do simplification here and here, and you come up with an overall real, let's call this real 5 plus imaginary 2. And then it's clear what is resistance and what is complex impedances. And you can do that iteratively until you can separate the components, because you know that a capacitor, well, you know that the resistor is going to be real, but you know the capacitor The impedance for the capacitor is going to be minus J omega C, and the impedance for the inductor is going to be J omega L. So if you can get these types of expressions, then you can extract whatever doesn't have this is going to be the value of the capacitor, and whatever doesn't have this, or when you take that away, that becomes the value of the inductor. So that's the procedure in general. Does that help?
Yes, it does. Thank you.
Any other questions regarding problem 1134? All right.